Reminds me of my high school Latin. For those of you who read Caesar, the Gallic conquest started off Gallia est omnes divisa in partes tres, which, so anyway, we're here in the third part. Just like Gaul was divided into three parts, so are these talks. I am listening to your questions and the pieces that seem to interest the students who I've talked to over dinners and so on. I redirected this a little bit to try and get more into both the observational validation, how you might check a parameterization observationally, which isn't an indirect process at best, and secondly, some biophysical feedbacks for these pieces so that hopefully some of you will find those pieces more interesting. So remember, the overarching theme is that the fundamental equations, which we know for fluids, the overarching theme is the Earth is forced on very large scales, and then there's some kind of process that flows the kinetic energy and other fluid properties down to small scales where dissipation can act on it. And we imagine that what we're simulating is somewhere in this middle range, but we can't afford to do the whole thing in one model. So we have to break the pieces up, and we know the equations on the smallest scales, and in particular we know these little exploding pieces that tell us about the molecular fluxes of heat, salt, and molecular stresses on the fluid. So this part is known. So last time we talked about simplifying the equations. This part, basically, to make a reduced model, to remove things like sound waves, pieces that slow down the efficiency of the model. Today I'm going to talk about parameterizations, which is developing this side, these little pieces, not for the motion of molecules, but for the motion of eddies or turbulence. So we're going to think of it the other way. We're going to say, what if the eddies behave like molecules a little? They should have some kind of law like this that describes their behavior. So I'm going to talk about two different flavors. One, mesoscale closure that gives you something resembling this piece, and then one submesoscale closure which gives you something resembling this piece. Okay? And why do I say closure? Well, without these laws, then this piece and this piece and this piece and this piece would be unknown in terms of the predicted variables density, velocity, temperature, and salinity. So since we're solving for the density, velocity, temperature, salinity, and pressure, and then these guys depend only on density, temperature, pressure, salinity, this system is closed, but only after we have the molecular laws in place. Does that make sense to everybody? Okay. So yesterday, although I didn't write them in this form, we talked about adapting, bringing in these wavy pieces, so having Lagrangian velocities. Oops. So this is the equations for fluid motion with a conservative temperature. That's the only change there. But here, this is the one with the Lagrangian velocities, the Lagrangian advection, Lagrangian Coriolis, and this Stokes shear force piece, so that we adapt our equations of motion to bring those surface gravity waves effect into the equations. Okay? So the question now is, we've still got these stresses, we've still got these salinity fluxes, heat fluxes. Those pieces we need to know in order to close the system. But we can't close them with molecular fluxes. We're going to have to close them with a subgrid closure for the turbulent process. Okay. So let's go back to our little picture here. Okay, so this, basically staring at this simple picture, remember we're forcing on the large scales, dissipating on the small scales, and a useful way to think of when the dissipation starts is when the Reynolds number equals 1. That's the velocity times the length scale over the viscosity is the Reynolds number. So this is when either the velocities are small enough, or the length scales are small enough, or the viscosity is large enough to damp at leading order. That's where we get to this dissipation. But if we're in a model where our grid scale is over here, say at much larger, at much smaller wave number, much larger scale than the dissipation scale, what we really need is some other manufactured pretend version of the dissipation with maybe a larger viscosity in order to dissipate over here instead of here. So we need to crank up the viscosity. So that seems like a simple problem, and what we most of the time do as our first guess is we just turn up the viscosity in the model until it stops blowing up. Because if you use this viscosity in a numerical model, it'll normally blow up. So we just crank it up. That's one way to do it. That's not a very satisfying way to do it because, one, we have to screw around with the model, changing parameters at the beginning, and the answer always depends on which detailed choice we get. And so we tend to be conservative. We don't want the model to crash halfway through, so we use a little bit too much viscosity, which makes it too damped. So instead, it's better if we could figure out a law that predicted how much viscosity we'd need based on the flow over here that was resolved. So if we knew what this flow was, we'd have a good sense of the velocity as a function of length scale, and then we could predict what viscosity we would need to damp it. Not too much, not too little, just right. So that was the concept that Smagorinsky developed into a scaling law for the viscosity for three-dimensional isotropic turbulence. That's the formula he came up with. There's a dimensionless parameter. There's pi, because that's, if you're really paying attention, you've always got to have pi in your formula. And then there's some derivatives of the velocity field. So this is the strain rate. And then here, importantly, is the length scale of the model you're using it in. So you change the length scale, you go to an adaptive grid, you go to a model that is nested. This tells you how you adjust. You don't have to think anything about that. Okay, so this is great. Maybe this is good enough. And in some sense it is, if we were simulating three-dimensional turbulence in the ocean. But the problem is, turbulence doesn't get to 3D in the ocean until you get to very small scales. Smaller scales than the mesoscale, because the mesoscale, as we said yesterday, was wide and flat in relatively shallow water, 100 kilometers wide, 4 kilometers deep. The submesoscale is 10 kilometers wide, 100 meters deep. That's not 3D turbulence. So we need to think a little bit about 2D, or even better, quasi-geostrophic turbulence, which is quasi-two-dimensional turbulence. And that actually has a similar idea, but a different flow behavior. So here, if we inject energy or other variability at an intermediate scale, in this kind of turbulence, the energy actually goes to larger scales. So mesoscale eddies, if you create them at 20 kilometers, will grow into 100 kilometers eddies. They'll merge together. The energy goes upscale. But in between the eddies, they'll shed these little filaments, and those little sinuous pieces will be chock full of another quantity called Enstrophy, which is the vorticity squared. So the vorticity squared goes to smaller scales, while the energy goes to larger scales. Okay, but it's sort of a technical detail about 2D and quasi-geostrophic turbulence. The idea is the same. Instead of dissipating whatever it is that's flowing from scale to scale in this turbulent cascade down here at small scales, let's truncate it at the grid scale and make it work. That idea, which is due to Chuck Leith in the 90s, he proposed a way to truncate two-dimensional turbulence over here, and then myself and a couple of very bright students adapted that to quasi-geostrophic turbulence and give this little closure, which now, that's not the right equation. That's Chuck Leith's version. But so it depends on the gradient of the vorticity rather than the strain rate, as we saw last time, because the vorticity is the key player in two-dimensional turbulence. But doesn't matter that much. These are sort of the details of how we think through the process of turbulence and different kinds of turbulence and propose different closures depending on where our grid scale lies, what kind of turbulence. So when we talked about the dimensionless equations yesterday, framing them in terms of the grid scale, this is why, is because you want to think of the dynamics that occur at the grid scale when you propose a closure. Okay, so what does it look like? So this is a bunch of simulations superimposed The black one is an extremely expensive, very high resolution simulation, and so that's our truth. Then there's a red one, which is our coarsest resolution, so it doesn't go down to the smallest wave numbers. It gets truncated somewhere over here. I mean, the largest wave numbers. It gets truncated somewhere over here. The green one is a little better, and then there are 3 different blue ones that are superimposed on top of this. And here, since this is a toy problem, it's just a channel run with turbulence in it, we know exactly what the forcing scale is because we set it as we set up the problem. It's somewhere in the middle. So in the ocean, this would play the role of our deformation radius, say. It's here in the middle. And if we don't resolve that scale, there's not much we can do. We're going to get a bad answer. So the red one and the green one, we don't expect those to work anyway. But the key result here is that all 3 of the blue ones lie right on top of the black one. So once we have resolved this mesoscale instability process sufficiently, it doesn't matter what resolution we use, we get the same kinetic energy spectrum at all the length scales. Okay? So, to put it this way, I have 3 different versions. So this is the QG Leith one, which is the one I just showed. This is our new theory. This is the 2D version that Leith came up with in 96, and this is Smagorinsky's version from 63, all on the same test problem, which is a standard kind of geostrophic eddies in a channel problem. And it's a little bit like Goldilocks and the 3 bears. So, she has porridge, and one of them's too hot, and one of them's too cold, one of them's just right. They're chairs, one's too firm, one's too soft, one's just right. And then the bears get angry and chase her out and say, don't talk about this anymore, we want our house to ourselves. So that's, what you can do in a few minutes. This one is too smooth. You can see all of the simulations are pulling away from the truth simulation. At the smallest scales, there's not enough energy. This one's too noisy. At the smallest scales, there's too much energy. And this one is just right. Okay. So let's put this in a real model then. And this is the work of Brodie Pearson, who's a postdoc in my group, has been working on this, and compare it. So this is a global mesoscale resolving simulation just to see what it does. This is a standard closure, and this is just a map of how much energy is being dissipated by the viscosity in the model. And so you can see the standard closure has a whole lot more red stuff than either the 2D version or the QG version, and this is the one that was just right. This is the one that was too noisy. This one would be way too smooth. And so by changing this, we allow there to be less dissipative dynamics in the same model. And you say, okay, this is all silly stuff. All the eddies here are resolved in all 3. And in some sense, they do all look like the real world. They all have eddies. The eddies are in more or less the right places. The Gulf Stream separates in more or less the same place, those kind of things. But is there any big picture difference? And so Brodie went and diagnosed the different methods for dissipation of energy in those 3 models. And so these blue lines, this is the standard closure, this is the 2D version, this is the QG version. So this is dark blue line is how much dissipation is due to that viscosity. This lighter blue line is how much is due to bottom drag, and this green one is how much is due to vertical viscosity in the interior of the fluid, and the yellow one is how much is vertical viscosity in the boundary layers, top and bottom. So you can see that when we change that viscosity closure, the amount of energy dissipated has dropped by a substantial amount. So when we talk about this idea that we have energy coming in from the sun and it's flowing through the Earth system and it's getting dissipated in different ways, the story has just changed from number 1 dissipation, number 2 dissipation, number 3 dissipation to number 1, number 2, number 3. The order of what is dissipating the eddies has changed. The eddies are no longer being dissipated by this viscosity. They're being dissipated by bottom drag and vertical viscosity, which we think is more physical. Okay? So this kind of thing is the sort of thing you worry about. All right, so let's summarize this piece, and then I want to move on to talk about the submesoscale, which is more interesting for the biology side. So this is what we do. We basically paid attention to that cascade. We paid attention to the ideas from quasi-geostrophic turbulence rather than three-dimensional turbulence. And that makes this a scale aware. It knows what grid scale you're using in your model. So if you change the grid scale or you have a nested grid, it knows how to adjust. It's flow aware. It's paying attention to things like the vorticity and buoyancy in the flow. So if the flow changes conditions at some latitudes is different than others, or in a boundary current, not in a boundary current, it knows. And it's not too noisy. It's not too smooth. It's just right. And at mesoscale resolution, it changes the primary sinks of energy. So it has a global consequence, not just this sort of like detail stuff that people like me like to think about. So are there any questions about this before I switch over to the submesoscale? Maybe not. Okay. We'll switch. This is maybe more fun. Okay. So we saw this picture. We saw this movie yesterday. And remember, this is the one that has Langmuir at the bottom and submesoscale at the top. And I showed you this little toy simulation here, and the fact that it affected the climate model, whether you included this submesoscale parameterization or not. I want to tell you a little bit. So I went back and dug up a bunch of slides from 10 years ago when we developed this theory to give you a hint of what we were thinking about at the time as we built it, and give you a sense of the information we had. So one primary piece of information we had was Walter Munk had been talking to an astronaut, Thomas Scully Powers, who had been taking pictures of the ocean surface from the space shuttle and just saw little spiral features everywhere in the world. Every time he got a good picture of surface glitter or surfactants or anything, it had these little spiraling patterns. And it was his take that they were dominantly cyclonic. So it didn't matter which hemisphere you took them in, they knew which way the Earth was rotating. And the scale of these is only 5 kilometers. So this was sort of magical. Nobody had any idea why there'd be any variability that knew about the rotation of the Earth at 5 kilometer scale. So one of the early simulations that I did had a feature that if you scale it to the same size, looks sort of like that. And so we got very excited to track this down. And so we looked at the statistics in this model versus a observational collection of the statistics of just cyclonic versus anticyclonic in the surface. Just a bunch of drifters. Which way did they turn? Did they turn with the Earth or against the Earth? And we got a PDF that was skewed in kind of the same way, so that it was a little bit more cyclonic than anticyclonic, especially the extreme events were significantly more towards the cyclonic side. So we thought we were on the right track. Another set of observations that was collected, so this is just a towed CTD, and they're tow-yoing up and down in the mix layer, and they did a wavelet power analysis. So for those of you who don't know how to read a wavelet variogram, I'll try and explain it quickly. This is sort of length along the tow this direction, and this is length scale going this direction. So as they're going along, they're chopping up the signal into things of 1 kilometer, 2 kilometer, 5 kilometer, 10 kilometer, 20 kilometer chunks. And the brighter red this is, the more energy there is on that length scale. And so this is the density variability along this tow. And you can see there's lots of density variability at large scales. Not surprising. There's mesoscale up there. There's lots of density variability because of the mesoscale. But as you go down and scale, at a certain point, there's almost no density variability below that. So some process down here knows that they're density gradients and is capable of eliminating them. So we have fronts up here at this scale, not so much fronts down here. So something magical happens at this range of scales, the submesoscale, that allows that energy to be released that's in horizontal density gradients. And so this Phil Hosgood, who wrote this paper, was clever enough to put the deformation radius of the submesoscale mixed layer on top. And you can see that the deformation radius of the submesoscale nicely delineates where the end of that goes. So now we have a lot of pieces in place. We know that these are spirals. They're not symmetric instabilities. They're spiraling things. They care about the deformation radius of the mixed layer. And so we set up this simulation, which I showed you yesterday. And what I didn't tell you yesterday is that this pulsing up here is because I put a diurnal cycle of heating and cooling on. And the reason why I did that was because I knew I wanted to have a mixed layer, because we knew there was something special going on in the mixed layer. So you can see the pulsing up there. And if you diagnose where the vertical and horizontal fluxes of density are, the vertical fluxes are all in the small scale features. That was interesting. That says submesoscale is doing something important in the vertical, and the horizontal fluxes were all in larger scale features. So the traditional idea had been that the mesoscale dominates everything because these eddies are so big, they transport everything faster than everything else, and that's true. But they're so big that they actually can't do much in the vertical. They're kind of constrained to be in the horizontal. One of the things you expect to happen as the Rossby number gets large is you expect to be able to make larger vertical fluxes. So the submesoscale, because it has a larger Rossby number, wins in the battle of vertical fluxes because it's able to be more vertically oriented than the mesoscale, which is constrained to be flat. Okay? So that was another clue we had. And then the last clue was I ran this simulation. So this simulation was spun up for 900 days and then interpolated onto high resolution, and then that's the piece you saw. At the end of 900 days, I also tried to turn off the diurnal cycle and see what happens to the boundary layer. And I was talking instead of watching, but you can see that in just a matter of a few tens of days, the mixed layer goes away, and the features become much smoother, larger scale. So that mixed layer being present and that smaller deformation radius that's associated with the mixed layer is apparently key to the existence of those small scale features. Let me play this one more time now that it's gone to the end. So small scale features in both, because they're spun up the same way. Still a mixed layer here, but it's not being preserved by a diurnal cycle, and so it restratifies itself and goes away. On this side, the diurnal cycle is still there, the submesoscale is still active, and you can see over here the features are getting larger and larger, and we're covering the standard channel, which just has mesoscale features top to bottom. So it was the existence of the boundary layer that made the submesoscale possible. Okay? And without the diurnal cycle, the vertical fluxes, I'm also tracking at this one versus this one, they're decreasing in magnitude as that boundary layer goes away. A lot of people show that the vertical fluxes either there or not there based on resolution of the model. This is not, these have identical resolution and identical initial conditions. The only difference is whether I leave that diurnal cycle on. So there's a coupling between the existence of the boundary layer from surface forcing and the existence of the submesoscale, and the submesoscale is the one that does this large vertical restratifying flux. Okay, so that simulation was kind of expensive, so we wanted to make a cheaper one, which is how I got to this little toy game that we saw last time, where we just put warm water on one side, cold water on the other, and let it slump with these little eddies. This is pretty cheap, cheap enough that by the end of this, I had run 250 simulations like this. So this 250 simulations allowed me to vary the mixed layer depth, allowed me to vary the strength of the front, allowed me to vary the rotation rate of the planet, allowed me to vary the subgrid viscosity, the subgrid diffusivity, allowed me to vary whether or not there was a diurnal cycle included, whether or not there was other boundary layer mixing like KPP or different schemes all put on, vary that whole set, and then look at the common threads that cross among all of those simulations. That was the way we got to. And these are the pieces that we found. So this is stratification in time for a few of those simulations. And what we saw is that at the beginning, there's inertial oscillations like you'd expect. Then those eddies grow. And when the eddies hit finite amplitude, zing, off goes the stratification. It starts restratifying. The eddies allow that front to tip over, putting warm stuff on top of cold stuff. And that's the next stage. Okay. So, these are just two at different resolution to show you that I was converged in resolution in the simulation. So 250 simulations all converged in resolution on that problem. Okay, so let's think now, like we did last time, in terms of the power spectrum. What's the turbulence doing as those eddies grow, and how does it become turbulent? So we actually knew what the linear instability scale was for that problem, and at the beginning, that was a good prediction. But by the time we get up to finite amplitude, that is, the time when we start restratifying quickly, the linear prediction is not a good prediction anymore. Finite amplitude is about here. So we have a turbulent cascade that's the agent driving this restratification. So previously we'd messed around with a few ideas for a parametrization, and they all were based around using the scale that we knew the eddies would start at. But when I made this movie, I realized it's not the eddies scale when they start, it's the scale that they have when they do the restratification that counts. So we wanted to step away from using the deformation radius as like a mixing length, which is what people had done traditionally before. So, all right, we can't use that result, so we have to do something different, which is hard to think about. So what is fixed about this problem is that it's all trapped within a boundary layer. So that's a fixed length scale. It's not a horizontal length scale, it's a vertical length scale. So we redirected our thinking to think, what if it's the vertical length scale that sets the size of the eddies? The eddies start doing something, and they are trapped to stay in the mixed layer, because we knew the mixed layer was really important. What if that's the thing that sets the largest eddy length scale? And so, when we hit finite amplitude, we wanted to know how fast are the eddies going when they hit finite amplitude. And as a rough approximation, the eddy velocity saturates near the kinetic energy that was in that front that it grew from. It was kind of a guess. Other people had used this saturation assumption before. That's one piece. This is actually the weakest part of this theory, which since then we've now figured out. And now here's the key length scale piece. The vertical excursions, that is the buoyancy anomalies versus the vertical buoyancy gradient, should scale with the depth of the mixed layer. So that's what set it our length scale. The length scale is set in the vertical, not the horizontal. Okay? And then the last piece is that the eddies tend to flux along the buoyancy gradient, but a little bit below. And that was sort of diagnosed. And that's all the pieces we need. So here's how the scaling law goes. We're thinking about a restratifying vertical flux, so velocity times buoyancy in the vertical on average, which is the same thing as the rate of potential energy change per unit time, or just delta potential energy per delta time, or change in Z, change in B, change in T. That's kind of just playing games with definitions. So the buoyancy exchange is just a partial exchange, so we're just swapping stuff around, and that gives us this consequence. So now we can change it either by swapping stuff in the y direction or the z direction. The flux slope scales with the buoyancy slope. That's what we just said about the slopes. So that changes the theory like this. The time scale is the eddy turnover time, which is a nonlinear measure of the strength of eddies rather than the linear instability time scale. That gives us this result. From the mean thermal wind balance, because the eddies are as strong as that front that they grow off of, and the vertical scale is known. You put all those pieces together, that's the scaling law you get. Okay? This is the theory. The theory says the rate of restratification goes like the mixed layer depth squared over the Coriolis parameter times the horizontal buoyancy gradient squared. Okay? So those are the ingredients that we had to get into it, and I'm running out of time, so I want to get to how this is. So then we said, okay, it's probably better to make this an overturning stream function rather than a vertical buoyancy flux for a consistently upward and horizontally down gradient flux. So this is kind of standard stuff following Jensen-McWilliams, which is an existing mesoscale parametrization, which is, a fun thing to bring that along. Let me show you how it looks. Okay, so we're proposing a stream function that turns over those fronts and lets them slump. That's what the eddies are doing. They're letting the front slump. So this is what the parametrization looks like. And this is what a simulation diagnosing the stream function on the fly looks like. And you can see this is a whole lot noisier and there are lots of problems, but roughly they're doing the same thing. And then this is showing the stratification of the mixed layer restratifying. And one of those lines, I forget which, is the full three-dimensional simulation and one is the parametrization. And you can see that they track pretty well for at least a little while. Okay? So this was all fun. This was kind of the GFD part of things. The fun thing was then we decided to figure out whether this applies in the real world. So we estimated where in the world that mixed layer depth squared times buoyancy gradient over Coriolis parameter was big. This is from observations. This is the answer. And so, wow, a lot of the Earth probably has this going on. That's cool. And this movie I put on my webpage, actually, and I had a bunch of observationalists make cruise plans based on where those bullseyes were. And I was like, don't trust me like that. You know, actually use some real information from someone who knows something about observations rather than this little movie. And we had to modify it a little to get ready for climate models. For one, you can't divide by F because F goes to 0 at the equator. So we put a mixing time scale in to fix that part. And for two, the horizontal buoyancy gradient in a coarse resolution model is just not as big as a fine resolution model. So we built in a little bit of scale awareness to correct for that factor. So it's like the little fronts that the eddies grow off aren't resolved. So the coarser fronts need to be scaled up into the equivalent finer fronts. And that's where this result comes from, which I won't discuss in great detail. But that's the piece. So now what else does this thing do? Well, you put it in a climate model. It does other nice things. It reduces the bias in CFC uptake for the subsurface ocean. Okay, why is that something that's interesting? Well, CFCs are something we can observe easily, and we know the whole time history because humans make it. It doesn't exist naturally. So if there's CFCs in the water, we know where they came from. So we have a perfect record with a clock on it. This improves that, not because it's changing anything about 2,000 meters, but it improves it because it changes the boundary layer depth, which changes the air-sea flux, which improves the transfer of gases from the atmosphere to the ocean. Okay, so that was a good clue. And here's one of the nicer pieces of observational validation. It was done by Leah Janssen, who's a student at the University of Washington. She realized that if you do this eddy slumping to go from a condition that looks like this to slumping over, or if you allow the sun to re-stratify that boundary layer, you would get a different consequence in salinity temperature change. And so she analyzed the salinity and temperature changes from all the upper ocean observations in the world that were easily accessible and made this map where this color of green could have been either because of the sun or the eddies. This color blue is only consistent with the eddies. And this color, no model fits. And this orange color is where the 1D process probably wins. So now you have a map of where in the world this process actually looks like it is consistent with the temperature and salinity observations. It's a little indirect, but this is kind of a nice way to take observations and figure out what's going on. Is there a biological impact? Well, possibly. We started looking for these spirals on the sea that Monk had noticed in ocean color. And in chlorophyll band in particular, you can see that a lot of these small-scale features show up in chlorophyll and show up in diatom blooms. Now we have lots of pictures like this. We didn't back then, but we do now. And so you could say, well, these little mesoscale features, are they there because nutrients are being affected, or are they just there because they stir everything on that scale, which they do? And the key idea is that when you work through that parameterization, the scaling for a typical vertical velocity scale is 20 meters per day, which is really fast in comparison to other things. So when you think about the mesoscale eddies, you don't get anywhere near this. So these small submesoscale features, because they dominate the vertical fluxes, can dominate the vertical fluxes for the supply of nutrients up into the light as well. And if you look at observations of chlorophyll levels versus what was a state-of-the-art chlorophyll prediction from a global biogeochemistry model, the places where there are big errors are in light-limited regions. There was too little biomass which is exactly what you'd expect if you were not restratifying sufficiently quickly to put the nutrients up into the light and to keep the phytoplankton living in the light for their lifetime. So this, again, is not a proof. There are lots of other things that are wrong with this model aside from not having submesoscale, but at least we had a target that we were kind of hooking on together. And then a few years later, there was the North Atlantic bloom experiment where they went out into the North Atlantic and waited to see when the phytoplankton start. What's springtime for phytoplankton? The wintertime, they don't grow very well because the mixed layers are too deep and they're hidden from the light. And the springtime, the light comes up and the mixed layers restratify and bing, they bloom. And there's a huge bloom in the North Atlantic. So they went out and measured the North Atlantic, the bloom itself, but also the horizontal density gradients and mixed layer depth at the same time, so that you had all of the key parts to wonder whether these submesoscale eddies were involved. And then they did a model. So here are the observations. The red line is what happened. Here is another set of observations. The green line is also what happened, I think in a slightly different location or different smoothing. And then in regions where there was not a gradient, a horizontal gradient, the bloom didn't go as fast or as early. And if you model the restratification process, and you guys can ask Amala Mahadvan, who's going to be here on Saturday, about this in more detail, if you include the horizontal gradient, the data sits within the range of model predictions. If you don't include the horizontal gradient, the springtime waits until later. So essentially what's happening is that restratification occurs about 3 weeks early because of submesoscale eddies. If they weren't there, you'd have to wait until the sun got a lot stronger to restratify the same boundary layer, and the sun got a lot stronger to make the light kick off this bloom. Okay? And so, inspired by that kind of thing, we started releasing biological, and I will put very big quotes on biological. From my perspective, this is a passive tracer into these kind of high resolution models to see what they do. And you can see both the implant of Langmuir circulations. This is just tracer concentration for a tracer release near the mixed layer base, quasi-nutrient-like tracer. But you can also see submesoscale features. So both the submesoscale and the Langmuir stuff that we've been talking about has a direct impact on the transported tracers within the boundary layer, which is also known to biologists as the euphotic zone. So this whole game is coming back to having a big impact there. Okay, I'm running out of time, so I'm going to tell you, I already told you the one biggest flaw, I think, is this assumption. So a lot of people have been working on trying to make better assumptions about where the velocity scale should be. One of my students did a very detailed analysis that said if you do have that velocity scale, you can do a lot better than our scaling law. You can go from the kind of blobby gray one here to the black straight lines if you just know what the velocity of the eddies is. But you don't know that in principle. And the last piece I'll say is, so we also talked about this simulation and Langmuir stuff, and we had this, and I would love to have another opportunity to tell you all about how we developed on a similar kind of 10-year time scale, a Langmuir parameterization that allowed us to do this, but I don't have time. So let's conclude. Okay, so the equations of ocean motion are known, but when there's sufficient resolution to contact the molecular fluxes, but we can only simulate about a teragrid. It's this idea 1,000 times 1,000 times 1,000 times 1,000 in terms of grid scale and time steps. So we have to pick it. The reduced models, like the wave average equations, help get physics in or help keep expensive physics out, like sound waves. But parameterizations help us bring processes that are unresolved in. But you have to know a whole lot about the behavior of the kind of turbulence in order to develop these, or the kind of biology, or the kind of fisheries. There are lots of parameterizations that we think about. It takes a pretty intensive process study level to get those in. Present parameterizations are viscous or advective. So the viscous one is the one, the QG Leith one we saw. The advective one is the one from the submesoscale, and sometimes diffusive. Actually, the submesoscale can be adapted into diffusive. So in this sense, it mimics those molecular flux laws. But it does not mimic them in that it doesn't keep the diffusivities constant. The diffusivities are a function of what's going on in the flow. And so they are scale aware and flow aware. Thanks very much.